All right. Hi, thanks everyone. I'd like to give a thanks to the organizers for giving me an opportunity to present my work. This was done in collaboration with Rick Persch, who you've met earlier, and Eduardo Martinez, who also spoke earlier today. And the goal of this project was to extend the entanglement harvesting protocol to the case of linearized quantum gravity. And so really quickly, just kind of an outline of how the talk will go is I'll give a brief introduction to the project and a little bit of background on our model of linearized quantum gravity, so how we quantize the fluctuations of a Minkowski background. Then we'll talk a little bit about our quantum matter and how this couples to gravity, discuss the entanglement harvesting from this gravitational field, and discuss some of the results that we found during our work. So we know for about a century now, we've been studying general relativity and quantum field theory. And there have been many attempts now to create a full theory of quantum gravity, yet we have not been able to do so. However, it is predicted that quantum field theory should describe gravity in the weak field limit. And so with that in mind, what we aim to do with this project is to probe the entanglement for a theory of linearized quantum gravity. The approach that we took to probe this entanglement is to utilize the Unruh-DeWitt detectors, and at this point, we've heard a lot about them. Now, Unruh-DeWitt detectors, as mentioned earlier, are useful for studying a number of phenomena in quantum field theory. So we can use them to probe the Unruh effect, probe spacetime topologies and geometries. We can use them to describe communication protocols in quantum field theory. And for the purposes of our talk, we can use them for the entanglement harvesting protocol from a quantum field. So knowing how we're going to approach this, we first want to describe the model of quantum gravity that we'll be using. So we're going to assume that we have a metric that will satisfy Einstein's equations to leading order. And we will assume that we're in a vacuum state, so T mu nu can be set to 0. And we will perturb this background spacetime by some small metric, gamma mu nu. And now, because we're working in the weak field limit, we'll assume that our background spacetime is Minkowski. And so our perturbed metric is then given by this expression here. We've kind of changed the notation a little bit. We've changed gamma mu nu to be this 8 pi LP H mu nu. This just allows us to have the same units for the field H mu nu as for other quantum fields. It's going to be useful for some of the comparisons that we make to the case of electromagnetism later on. And, we will choose to work in the traceless transverse gauge so that we can privilege an inertial observer with a 4 velocity 1, 0. And the result of this gauge fixing is that we get a wave equation for H mu nu that has 2 independent polarizations. And the expression is written here, and we see the polarization tensor epsilon over there is what gives us these 2 independent polarizations. And we also can show that the Riemann tensor can be written in terms of this new field H mu nu. And in particular, we'll see later on that these components that are written down here at the bottom are actually the ones that couple to a particle undergoing some inertial trajectory. So now the quantization we use for this field, H mu nu, is that we'll be promoting those coefficients in the wave equation to creation and annihilation operators, and we will impose that they satisfy the canonical commutation relations. And as a result of this, all of our gravitational observables will now be promoted to to operator value distributions. And again, for our purposes, we will be promoting the Riemann tensor to a Riemann operator. And so now that we kind of have an idea of how we're quantizing this linear gravity, we want to discuss our quantum matter. As these talks have gone on, apparently the drawings for particles undergoing inertial trajectories have been deteriorating, but we assume that we have a non-relativistic local quantum system, which is our particle here undergoing some inertial trajectory z of tau. And this detector has a free Hamiltonian H with eigenstates n, so that we're capable of writing the wave functions associated to each energy level as psi n of x. And the next thing we want to do is we want to write down how does this couple to our linearized gravity. Now, the first approach would be to write down an effective Lagrangian for our detector, and from there derive our coupling Hamiltonian. This was done previously, and the result was shown here. However, the big problem that we run into with this is that this is a gauge-dependent interaction Hamiltonian. To avoid this, there are simpler ways to get around this and to not have gauge-dependent theories. And for our purposes, we arrive at this expression here, which also should look familiar from Rick's talk this morning. It's one of the correction terms in his particle detector models. And we obtain a quadrupole coupling to gravity, where the m here is actually the mass of our detector, and x hat is the position operator associated to the wave functions of our detector. Now, to kind of get a more familiar approach to the UDW models that we've seen earlier, we can now expand this Hamiltonian in terms of the eigenbasis of our detector. And we notice that we obtain a smearing function given by the product of the wave functions. And we denote this by f and m. And further, to simplify some calculations later on, we have the coupling constant actually in this case is directly proportional to the mass of our detector, which is convenient when looking at cases where you want to compare to electromagnetism, because this is a much more tunable parameter in that we can kind of choose the mass of our detectors a little bit more freely. Now we'll restrict this to a two-level system, and we'll implement the switching function to create the full UDW model that we will be using. And what we arrive at is this expression here. Now, instead of typical smearing functions that are seen in UDW models, this model here actually has these smearing tensors, which kind of show up because of the quadrupole interaction with curvature. And finally, now we just need to put this into our quantized linear gravity. And this amounts to following the quantization scheme from before and promoting the Riemann tensor to a Riemann curvature operator. And then recalling that this operator can be written in terms of our field, h mu nu. And we have our interaction Hamiltonian that's used for the entanglement harvesting protocol and for any UDW model that may be associated to this theory of linear quantized gravity. So with all of this in mind, we can kind of discuss the entanglement harvesting protocol and how it works. So we assume that we have two inertial detectors, A and B, and they're space-like separated. This would be a typical picture that you'd see if you have two Gaussian detectors with some Gaussian smearing. The light cone is apparently very difficult to see here. And we will also assume that both of these detectors start in their ground states and the field starts in its vacuum state, so that we have some density operator that's given by this expression. Now, the final interaction Hamiltonian in this case will just be the sum of the individual detectors A and B. And we apply a unitary time evolution operator, following very similarly from what Jose described this morning, to evolve this density matrix, and then we'll trace out the field degrees of freedom to obtain a density matrix for our two detector system, and that's given by this expression here. Now, these LAA and LBB terms, these are excitation probabilities for each detector's A and B individually. All of the other terms, M, LAB, LBA, all of these are non-local correlations that are acquired between the two detectors. And mainly for the purposes of entanglement harvesting, the most important one here is the M term, as it will show up in some of our calculations later. And so because they're identical from now on, we'll just associate L to LAA and LBB just to remove a lot of these subscripts all over the place. And now we also want to talk about a way to quantify this entanglement. Now, because we have a two-level system, there are a couple of good entanglement qualifiers that we can use. There's concurrence and negativity are very commonly chosen in entanglement harvesting. For our work, we use the negativity, and this expression can be found to be this here. And what this really is saying is that the entanglement that's acquired between the two detectors is kind of a competition between these correlations that get acquired and the local noise that each detector is experiencing. And so what we did from here, right, having this equation for the negativity and having our models that we'll be using, is we looked at a number of different examples and quantified the amount of entanglement that's harvested in each of them. But we need to actually input a couple of parameters for this, right? So we need to know the shape of our detector. We need to know the energy gap between the two levels. We need to know the mass of the detector, which in this case is our coupling constant. We need to know the time duration of the interaction, and we need to know the separation between the detectors. So given specific parameters here, we have a couple of examples of what we saw. And so here's an example here where we just used a Gaussian smearing function. And then in the next case over here, we see that we have a Gaussian radial component and then kind of multiplied these by the spherical harmonics to account for angular dependencies and to capture some of the quadrupole nature of the coupling. And we do see that we can, in fact, harvest entanglement from linearized quantum gravity. So with this in mind, we actually wanted to kind of give a real physical scenario that could eventually be possible to do. And to do this, we studied this model using hydrogen-like detectors because they're capable of fully capturing this quadrupole coupling, again, given that they have these spherical harmonics attached to them. And what we found is that the relative orientation between each of your atoms, because you have two atoms and we're picking a z-axis for each of them, the relative orientation between these two z-axes actually plays a crucial role in how much entanglement can be acquired between the detectors. And this was also seen in the dipole interaction from electromagnetism when this was studied by Eduardo and Pothas in 2015. And so what we found using this is that we were, again, able to harvest entanglement using hydrogen-like atoms. However, this was found to be about 25 orders of magnitude lower than in the electromagnetic case, which wasn't terribly surprising given that the electron states are much more sensitive to E and M than they are to gravity. And we also found that there's a very strong dependence on the amount of entanglement that's harvested due to the relative orientation of these detectors. And in fact, there are cases where it completely prevents entanglement harvesting altogether. We also found that because we're able to tune the coupling constant, right, by increasing the mass of our detectors, that we can show that there are some parameters where it should be possible to harvest more entanglement from the gravitational field than from the electromagnetic field. So some of the takeaways from my talk that I hope stick with you are that we haven't extended the entanglement harvesting protocol to the case of the gravitational vacuum. We have some cases where it should be possible to harvest more entanglement from the gravitational field than from the electromagnetic field. And from Eduardo's talk earlier this morning, that experimental verification of this could in fact reveal some predicted quantum behaviors of the gravitational field. Thank you for listening. Okay.
Hi, thanks for the talk. How do your results depend on your choice of gauge?
Yeah, so we choose to fix the gauge before quantization. We could go about this and quantize and then fix our gauge. The effects of doing this don't actually do anything to our entanglement harvesting protocol. The effects of gauge fixing later actually show up to fourth order in our calculations, and so we wouldn't really see any effects from that.
Any other question? Try to make questions short, so please.
Okay, so this is a comment which is shorter.
Okay.
No, I just wanted to mention that there are issues with the position operator if you want it to be relativistic. I don't know if you're aware, but for example, position operators do not commute with each other and things like that. So I was wondering if you consider this, sorry, it became a question, if you consider this during the construction of your interaction Hamiltonian.
So I'm not, I don't think I don't think we considered it too much. Again, this was the position operator associated to a system that was non-relativistic. So the detector itself isn't a relativistic system. So in that case, we didn't really concern ourselves too much with the relativistic effects of the position operator itself.
Okay, people, there is a question in the end.
Hello, thank you very much for the talk. I was wondering a little bit about the perturbation theory you're using here. Okay, so what is the perturbative parameter?
Sorry,
What is the thing that is small here?
so I mean, are you talking the perturbation of the background spacetime or the perturbation theory used for?
They're different.
Yes.
Okay, yeah,
Yeah.
that's why I was wondering,
Yes,
because the
so-
fluctuations are quadratic in the amplitude of the
Yeah,
gravitation.
so the perturbation for the background spacetime is just the field that we actually decide to quantize, and then we have to do perturbation theory with the interaction Hamiltonian to arrive at expressions later that we can use for results.
Yeah, well, yes, I just was wondering that because, okay, I can carry that. Because, well, I mean, so if the fluctuations are quadratic and that determines the entanglement, then you would think that you would have to consider also quadratic corrections to the metric, right? And that's more complicated because the fixing the gauge and all the stuff is way more complicated than in the linear case. So I was wondering if that plays any role. It may not play any role because maybe it only affects the coherent states or whatever, but.
I honestly, I don't think we gave it, I don't think we thought too much about it during this project. If I'm out of time, we are more than welcome to discuss this during a break. I don't want to take up too much more time if I don't have any.
Sure. That is a very complicated question, so let's move that after the break. So we've got another quick question here.
I think it's just the comment that will stay a comment. That maybe you could calculate a gauge invariant quantity. Okay, that's the comment.
Thank you.